Okay, now we're recording. Okay, so osteology, arthrology, and biomechanics. We have 4 lectures here, and I'm going to try to keep all 4 of them way under an hour each in some cases. Osteology is big enough that it needed 2 lectures. So let's go ahead and start osteology lecture, part 1. So this is for general human anatomy, and if you're taking a combined anatomy and physiology 1 and anatomy and physiology 2 in that format, places like USC, UCLA Nursing School prefer that. This would be the material we would also cover in that class. Okay, so like I mentioned before, anytime you see the word osteo in something, it refers to bone. Let's shrink let's maximize this image here. So the skeletal system, it's the second organ system we study after the integument. Remember, body regions, terms of direction, cells, cell division, those aren't organ systems. That's just some basic entry-level stuff. Once we hit the integument last lecture, which of course was a cutoff point for the last lecture and lab exam. What I'm starting today is on a lecture and lab exam, the next one here. Things get a lot more complicated, especially in lab in some cases, just because of the sheer number of bones, and after that muscles, and after that regions in the brain and parts of the nervous system involved. So the skeletal system, it's considered an organ system. And remember, an organ system consists of multiple interacting organs. Each and every single bone is considered to be a complete functional organ, just like the heart, lungs, liver, brain, pancreas, kidney, spleen, you name it. So the adult human skeleton consists of 206 discrete, identifiable named bones. And again, I have a word list posted on Canvas for a complete listing of these. That word list is in the lab shell of the course there. Babies can have more. I've seen estimates ranging from 224 to 232 bones at birth. This number is going to shrink because a lot of these things are going to fuse together into one unit very, very early in that person's life. All right, so the function of the skeletal system, taken as a whole, all 206 bones. The skeletal system, first and foremost, functions in mechanical structural support. We got all this soft tissue stuff, muscles and other organs on the body. We kind of need a rigid framework to attach them to, otherwise we're just going to be like a big blob on the ground. So that's what our skeleton is for. Mechanical support just for movement, never mind even being able to stand up and not melt into a puddle. Muscles need something to act upon when they generate their physical force. They need a hard surface on which to pull so we can actually move our body parts in whatever way we need to move them, whether it's writing a term paper, doing finished carpentry, driving a race car, or just gaming on a console or a PC platform. Doing all that stuff, you got to move muscles, and those muscles need something hard, a bone, a skeletal element against which to utilize to generate their force. Now, number 3, soft tissue organs are vulnerable to bruising and trauma. Really important things like the brain, heart, and lungs, those are typically protected in a hard bony shell. Heart and lungs have the rib cage, vertebral column. The brain has the cranium of the skull. So protection of some very highly important soft tissue organs is also the job of the skeletal system. Now, these next 3 are equally important, but they're more functional in nature in terms of physiology and homeostasis. The bones make red blood cells, which is kind of the biggest, most important element of blood in terms of function. I call red blood cells erythrocytes. Well, actually, I call them RBCs. The rest of the world may call them erythrocytes. Erythro means red, cyte means cell. So erythropoiesis, very specifically, the skeletal system, the bones make red blood cells. White blood cells are made in lymph nodes. Blood plasma is just tissue fluid. Platelets, those are going to be made elsewhere as well. Number 5, storage of calcium and phosphate. Yeah, we do need calcium for our bones, but if our heart goes or our nervous system goes without calcium for 1 second even, stuff breaks and stops working. We really, really need calcium on a millisecond by millisecond basis in our body, in the heart, and in the nervous system for proper nervous system function, proper cardiac cycling. And then phosphorus and calcium run low, not a huge problem on an immediate time frame. We can rob the bones of calcium and phosphate, well, calcium mainly, to keep the heart and the nervous system working properly. Number 6, regulation of some energy pathways of metabolism, possibly some fat burning metabolic pathways. The skeletal system, the bones release a hormone called osteocalcin. If you had done a Google search or DuckDuckGo or Bing or whatever internet search engine you prefer to use on osteocalcin a few years ago, 10 years ago, or 5 years ago, you would have gotten the NIH, National Institute of Health website, and they would have had a few peer-reviewed research papers on there. Do that same research a few years later, you get shunted to some pharmaceutical company's new product. And now I just did it about 6 months to a year ago, and boom, a whole bunch of research, all accessible on US government websites, pertains to this hormone produced by the bones. You do not think of bones as being a part of the endocrine system generating hormones, but apparently they are, and this hormone is somehow involved with mobilization of body energy reserves, breaking down fats, stuff like that, affecting blood sugar levels as well. Okay, so that's it for the function. Let us deal with the structure, the very generalized structure of bones. So, let's see, actually, yeah, okay, we're good here. I have a box of bones. I'll be doing some recordings tomorrow for our bone lab. So we're just going to go with some simplified diagrams here. General stylized diagram of a long bone, something you might find in the arm, leg, back of your hands, digits, even in your fingers. This particular bone, as I have it drawn here, looks like something you might find in your foot, in the metatarsal region, or in the back of your hand, the metacarpal region. So these bones, the central part is called the diaphysis or shaft. And then the very end, the epiphysis, that is typically going to be separated from the diaphysis by a zigzaggy squiggly line. It might be kind of faint. On real bones, you can see these real well. On the plastic models, even the cheap plastic models usually show these squiggly lines here. These are called epiphyseal lines, and they denote the location of what we call growth plates or epiphyseal plates. In us grown-ups, they've solidified. We're not doing a whole lot of longitudinal bone growth. But in kids, children, these are the site of what we call longitudinal bone growth, where the bones are getting longer. You all know how little kids, at some point, it seems like they're outgrowing their clothes in literally right before your eyes in real time when they go through those growth spurts. Well, when kids get taller, their arms and legs get physically longer, there's a lot of longitudinal bone growth at the epiphyseal growth plates. Okay, so the diaphysis or shaft, if we were to sort of saw this bone in half, on a bandsaw, a table saw, we would see that the interior of the shaft is hollow. And in real life, this hollow space is called the medullary cavity, and it's filled with fatty tissue. And this fatty tissue forms what we call yellow bone marrow. You order a certain cut of steak or pork, you get that yellow bone marrow inside the bones, and that stuff is super, super, super delicious, especially if you're a keto bro. Now, the ring, the cylinder, the tube of bone that surrounds the medullary cavity is made of really solid, dense, rock-like, stone-like material. Yeah, not your typical biological tissue. It's dense bone tissue. The epiphyses, these are filled with what we call spongy bone tissue, also known as cancellous bone tissue. And the material inside here is like you have a whole bunch of little spikes or struts. Yeah, I'll admit the people into the meeting. That being said, this is just being a recorded meeting. So if you've already taken the exam, sure, sit in on this. It's not a problem. But if you have not taken exam number 1 yet, y'all need to be seriously worrying about that, because what I'm talking about now is exam, not on the first exam. This is on the next exam. Anyway, so this spongy bone tissue, it's just like these little struts or spikes of bone going every which way. And the material inside here, this is called red bone marrow, also known as myeloid tissue. This is where red blood cell synthesis is going to occur primarily. That being said, if you need to make a lot of red blood cells for whatever reason, you just donated blood, you were in an accident, you just started some major changes to your workout and you're really amping it up, you can also make blood in the yellow bone marrow as well. But usually that occurs, erythropoiesis is occurring on the ends in the spongy bone tissue. Now, the very surface here of the epiphyseal areas is covered with not paper thin, but think about 2 index cards of cardstock thin. So about 2 index cards, 3 index cards thick, a thin wall of bone, and that's called, or I should say a thin layer of bone, that's called membranous bone tissue. Okay, so if you look at real live bones in anatomy class, if we were meeting in person, you would see that, oh no, we're not going over the first exam. No, that's due very shortly. So anyway, so this bone, the real bone specimen material is insanely fragile, without collagen protein there to reinforce it. You look at it, you don't want to drop these on a hard surface like the countertops we have in anatomy lab. Okay, so this is a up-close photograph. I had this nowadays. This was taken with like a fairly mid-grade Nikon DSLR. Now your average smartphone, your average your $99 Androids will take pictures at least as good, if not better. So the technology's awesome in that respect. But this is the end, what we would call the proximal end of a femur. Now, we got the dense bone tissue right here. So this is a real bone that's been sawed in half and it's sitting in a display case. So you got the dense bone tissue here, and then you got the spongy bone tissue here. What I have here are 2 photomicrographs, a photomicrograph of dense bone tissue and a photomicrograph at lower power magnification of spongy bone. And the spongy bone here stains pink. The area in between the bony spicules where red blood cell synthesis occurs, the myeloid tissue, red bone marrow, that's the purplish material here. Okay, and then if you can sort of, I guess we can, you know what, I'll zoom in on a subsequent image. There we go. So here we go. This is the distal end of the femur. Cross-sectional cut through the shaft or diaphysis, showing the medullary cavity, a nutrient foramina passageway, and then the dense bony tissue around there. But this distal end here, you can see that these little thread-like struts of bone, looks like this weird little reticulated network here. That's the spongy bone. And you can see this area right here. I guess I can blow this up. These images were like, I forget what, I think that SLR I used was 20 megapixel res. All I know is these files were insanely huge. They were bitmap files. I had to save them as a JPEG or PNG file because otherwise Canvas would crash, PowerPoint would crash, everything would crash anytime you try to open this. Anyway, you can see this thin layer of bone just on the outside, the spongy stuff on the inside. This, I'm highlighting it with the cursor, is membranous bone tissue. Okay, and of course we got a thin layer of membranous bone tissue right here. So this layer you're looking at, again, 1 or 2 index cards, not plain paper that you put in the copy machine, but index cards. That's about how thick this stuff is. Okay, let's shrink this bad boy back down and go to the next image. So these trabeculae or spicules, whatever you want to call them, they orient themselves in a very specific fashion along lines of mechanical force or stress, if you want to call it. And if in some cases, in some bones, you look at the way they're arrayed. Let's go to the previous image. Yeah, this one doesn't show it as much as others. This one kind of shows the same thing, sort of reminiscent of the of basically how Gothic era cathedrals. So we're talking about Europe in like the 1200s, 1300s, 1400s, 1500s, 1600s. You know, basically 400 to 800 years ago in Germany and France and places like that, sort of how they built these giant, in some cases, 500-foot tall cathedrals. And these stone members here are organized in ways that are reminiscent of the way spongy bone tissue goes together. Okay, now, dense bone tissue. So where do we find that again? Right down here where I'm circling with the cursor is the dense bone tissue. If we were to look at that under a microscope, which we did when we covered histology, connective tissues, and then I said, we'll cover this in greater detail when we deal with bones, which is now. What you're looking at here is basically like the end of a stack of sections of pipe that you might find at the Home Depot or Lowe's plumbing section. Okay, so cross-sectional view, you have these cylindrical pieces, like pieces of pipe stacked on a retail display. And if these are bone, well, first of all, in a dense bone tissue, these cylinders of bony material are called osteons. You may also call them Haversian systems. I just call them osteons. That's what I grew up calling them. And I don't know if anyone calls them Haversian systems. So ECM, extracellular matrix, is largely calcium hydroxyl phosphate, calcium hydroxyphosphate. You got calcium, 5 atoms of calcium, 3 phosphate groups, and part of a water molecule called the hydroxyl group, OH. So what this does is it makes bone like rock, like cement, like tile, like plaster, like concrete. It gives it its compressive strength, and it makes it really, really hard. Okay, so on this little photomicrograph here, you're just looking at one of these pipes or osteons or cylinders of dense bone tissue. And in the center, you have what's called a central canal, that dark spot. Well, there's a blood vessel in there. So this dark space in the center, you can call it a Haversian canal. I always called it a central canal. And again, there's a blood vessel in there that's bringing by glucose, or if you're a keto bro, ketone bodies, and of course, oxygen, big time oxygen. Now, when we look at this stuff on a microscope, it's been cut and polished using similar equipment to what a gem cutter would use to cut and polish gemstones. So it's basically dried and then cut and then ground, polished smooth on a lapidary wheel. And you'll see these little, first of all, you'll see this dark circle or oval in the center. Then you'll see these concentric rings around it. These concentric rings surrounding the central canal are called lamellae, which is a fancy Latin word for layers. And there's cells that we call osteoblasts, B as in Bravo. So this is very important here. This always gets a few people on the exams. Osteoblasts. You think that something with the word blast in it would blow stuff up, not build things up. But osteoblasts build cells. So the B is for build. Okay, now once those osteoblasts are done with their construction work, they're going to go away, or they'll just transform into what we call osteocytes, which are like the caretaker maintenance crew. They're just the on-site management company that takes care of the bone tissue. They maintain it. So they live in these little spaces called lacunae, similar to the lacunae that chondrocytes live in cartilage. Now, you'll see some tiny little spiderweb-like cracks radiating outwards from the central canal all the way to the edge of this osteon here, going through all the lamellae. These are really, insanely microscopic passageways. They're called canaliculi, kind of like little canals, little passages. And these osteocytes being kind of trapped in their lacunae, which is, you imagine being buried alive in a coffin or living in a little cave somewhere, just eating food and breathing air through a straw. That's sort of how these osteocytes are. So these little canaliculi are like the straws that allow oxygen and nutrients to get to them. Otherwise, they die. Now, let's go back to the outside of a bone here. The surfaces of a bone that will mesh or articulate against another bone, say the tip of your leg bones that join at the knee. These surfaces are called articular surfaces. They're covered with what's called articular cartilage, which in almost all cases is going to be hyaline cartilage. Okay, so at the end of a chicken bone, you get that shiny translucent material at the end of a drumstick or a thigh or whatever. That shiny grayish white opalescent translucent material, that's hyaline cartilage, macroscopically viewed by you without the aid of a microscope. Now, the rest of that bone is going to be covered with dense, irregular connective tissue, and we have a specific name for this. We call it periosteum. Okay, so that's the non-articulating surfaces, basically all the rest of the bone. Okay, so let me just double check the chat here. When I was a kid, they told me that, well, my mom told me, and like she just believed whatever she saw on TV and read in the magazines at the store. And we all know that you do not want to go believing that stuff, or your life will get very bad very quickly in a matter of a few years. I'm always popping my joints. And as far as I'm concerned, I don't think it damages them one bit. You know, it gets things circulating, because that articular cartilage, it's hard to nourish. And the way to nourish your cartilage, especially if you're like me and you've had a sports injury that's really bad, work your joints gently, low impact, like cycling and swimming. And, if it's okay to do so, you can pop them. My thumb, my hands are popping, my digits are popping like crazy right now, because I was up on a ladder with a cordless driver drill, driving in 2.5, 2-inch construction screws into a plywood sheathing. So, oh my God, I got a brutal hand workout for the last 4 days doing that. Anyway, if you look up close and personal at the bone, you got the medullary cavity here, dense bone tissue, and the dense collagenous connective tissue. Let me just double check the chat. Yeah, I know, I'm always popping mine too. And, once we all get red pilled at some point in our life, or some people get red pilled. And once you do that, you start questioning everything you were ever told, especially if you get red pilled about stuff like keto diets. Is cholesterol really a big deal or is it not a problem? Are vegetable-based corn oil, grain-based oils, soy oil, canola, all that stuff, is that really good for you? Once you get red pilled on that stuff, you start doubting everything you've ever heard. And now I feel like popping my joints. I will. I don't think it's bad. Anyway, so we have the periosteum on the outside here. Now check it out. We have these little collagen fibers that go into the bone where the osteons are, and we call those perforating fibers or Sharpie's fibers. I like the name Sharpie. That sounds like the name of a guy that makes a lot of money shooting pool. We had pool tables where I went to college. And one of the things that increased my grade point average was I had some eye damage from being out in the sun in high mountains or something. And I started getting astigmatism, but I was just a kid, too poor to get new glasses. So I couldn't shoot pool very good if my glasses prescription was bad. So I stopped playing pool and video games then in the arcade we had there on campus. And my grades got a lot better. Otherwise, man, I was shooting pool for like 4 to 6 hours a day, 8-ball mainly, sometimes 9-ball. Okay, hey, I mean, in school, they had tournaments for money and everything back then. If you go to a 4-year university, one of the selling points about going to a 4-year college is the awesome recreational center or gym. UC Davis has a spectacular gym, recreational center. Cal Poly Pomona, Cal Poly San Luis Obispo, UCLA, USC have spectacular, just magnificent centers. Or I don't know if Cal Poly Pomona. They had a video arcade there. I forget where exactly it was, downstairs in the student lounge. That place has changed so much. But at any rate, stay away from those places. They're bad for your GPA. Concentrate on studying, less on playing. Otherwise, you're going to be like me, and you're going to take way the hell more than 4 years to get that bachelor's degree. I ain't going to tell you how many years it took for me to get that bachelor's degree. If I'd stayed out of the video arcade, stayed away from the pool hall, I probably would have gotten a master's degree in the time it took for me to get a bachelor's. FYI. Okay, so what perforating fibers do, think of them as like steel rebar in steel reinforced concrete. They allow this hard, rocky, stony substance to flex and bend. You don't think of concrete as being like a piece of wood able to flex and bend, but steel reinforced concrete can do that. Bones can do that because of so much collagen embedded in them. So you could argue steel reinforced concrete in human bone tissue kind of behave the same way. Flexes and bends like a palm tree in the wind, yet it's as hard as stone. And we're building skyscrapers that are, well, in China and Malaysia, they're Dubai and Jeddah, they're already building some like 3,000 feet, 2,000 feet tall. These are pushing there. You don't think of buildings as being able to bend and flex. You don't think of bones as being able to bend and flex. But with that collagen fiber, the collagen content in them, they really do. Okay, so that's it for this lecture number 1 on osteology. What I am going to do is pause. Actually, you know what? I'll stop the share and let me stop recording.